Now let's discuss here the malus law. What is malus law? Right. First I'll write the statement, then I'll discuss with you what is malus law. See, when a completely plane polarized light beam is incident on analyzer, the intensity of emergent light varies as the square of cosine of the angle between plane of transmission of analyzer and polarizer. See, what is analyzer and what is polarizer? I can say one which polarizes is called polarizer, and one which analyzes the light whether it is plane polarized or not, we call it analyzer. In fact, the device is same. We call the same device as polarizer when it is polarizing unpolarized light, it is producing a plane unpolarized light, it is producing a plane polarized light from unpolarized light. Suppose you have a nickel prism, right? You have the nickel prism. When a beam is falling on the nickel prism, then what will it give you? It will give you a plane polarized light. It will just going to give you a plane polarized light. So this nickel prism will behave as a polarizer because it polarizes the unpolarized light. It polarizes the unpolarized light. On this side you have unpolarized light, and on this side you have polarized light. So nickel prism behave as a polarizer. This can be even nickel prism is one of the device. There are other devices also. You can have it as a set of glass slab and produce a plane polarized light upon refraction that we have seen in Brewster law. It can be Polaroids. It can be Polaroids also. So it can be any device which polarizes an unpolarized light and produces a polarized light, which produces a polarized light from the unpolarized light. So it can be any device. It can be say nickel prism. It can be set of glass slabs which produces polarized light upon refraction. It can be Polaroids, right? When you use the same device for analyzing the light to check whether the light is polarized or not, then that's called analyzer. You will see here, we call it analyzer. Now polarizer is defined by what we call plane of transmission, or simply call it path axis. In fact, light on this side is unpolarized, means different rays are vibrating. Different rays has got the electric field in different direction. Different rays are having the fields in different directions, having the field vibrating in different direction. But when it come out of the polarizer, they all will be vibrating in the same direction. They all will be vibrating in the same direction. This direction is called path axis, or this direction is called plane of transmission. So polarizer will be always characterized. We have a very curious question that if you have a unpolarized falling on the polarizer, then it will produce polarized light, but what will be the direction of vibration? What will be the direction of vibration of the light? So direction of vibration of the field associated with the rays forming a beam actually lies along the direction which is called path axis. Suppose if this is a path axis, then light coming out will have this vibration. So that's called path axis. If suppose the path axis is, say, if this is a polarizer and path axis is like this, then it means when unpolarized light is falling on this, the light which will come out will have all the vibration will be lying along the path axis. If this is path axis, then this will be the vibration. This is going to be the vibration. So this, we call this as path axis. It's also called plane of transmission. Sometimes it is called fast axis. So whatever be the name, you have only one thing associated, that is path axis or plane of transmission, or sometimes you also call it fast axis, right? That's about the plane of transmission. Now let me discuss about the malus law. Suppose I have a polarizer over here. Suppose this is a polarizer. Right? Now let me draw a path axis. Suppose path axis is vertical. Now light emerging from this, obviously say this is your incident light. So when light is coming after this polarizer, suppose this polarizer, initially this is unpolarized light having the field vibration in all direction. Now after it comes out, the light will be having the field vibration parallel to the path axis, right? It will be parallel to the path axis. Suppose I write this field as, suppose I call it Z, right? So I can write this as E naught and say call it I direction. Let me call it, this direction is I, right? Say this is X axis, this is obviously Y axis, and this is Z axis. So E naught I sine, this is how I can denote this field vectors, right? Now let's suppose we have an analyzer over here. We have an analyzer over here. So this is the electric field, right? Now suppose the path axis of this analyzer, this is your analyzer, and the path axis is going to be like this. Path axis is, so it makes an angle of theta with the, so it makes an angle of theta with the path axis of polarizer. So it makes an angle of theta with the path axis of polarizer, right? So this is theta. In that case, see the field vector, this field vector will be, this is going to be the electric field. Electric field is E equals to E naught cos kz minus omega t, right? So in that case, this field can be split into, I can split this into, say, along the path axis of analyzer and along the path axis of polarizer. Along the path axis of analyzer, say it is x dash, this is y dash. Then if I can write this as E equals to, along the path axis it will be E naught cos theta. Along the path axis of analyzer, the field will be E naught cos theta sine kz minus omega t. So this analyzer is going to allow only this component, the component which is lying along the path axis of analyzer. So here their field will be, here the field which will be coming out, the light which will be coming out, it will have the component of field. Basically this analyzer is going to allow only the component of field which is lying along the path axis of analyzer. So when it comes out of the path axis, when it comes out of analyzer, in fact what you have is like this, right? What you have is this one. So your the light which is coming out will have all its field along the path axis of analyzer, will have all its field along the path axis of analyzer, right? So it will be E equals to E naught cos theta sine kz minus omega t, right? So intensity here is E naught square, intensity here is E naught cos square theta. It will be E naught cos square theta, right? This will be, intensity will be E naught cos square theta. So intensity which comes out of analyzer is, if this is I, this is I dash, so this will be I naught cos square theta. That's the malus law. It says the intensity of emergent light varies as the square of cosine of the angle between plane of transmission of analyzer and polarizer. Square of the angle between plane of transmission of analyzer and polarizer.